first talk will be on the Rust language and its type system, a demo by Felix Clark.
All right. Hi, everyone. Can you hear me? Okay. This is a talk on Rust. It's a demo. I don't really know how to run a demo, so I've got slides, but as part of this, so first let me talk about the motivation for why Mozilla is working on this. It's a new programming language called Rust. The motivation is that to implement a new next generation web browser as part of the Mozilla research. It's a Mozilla research project, a researchy web browser, very much so right now. We're using and implementing a new programming language called Rust. And I said this is a demo, so as part of the talk, I'll periodically at least be able to go and show you the Rust language, because there's no excuse for people to go out and try Rust themselves unless their web browser doesn't fit on the window that they're using to render things. Because we have it's freely available to download, and importantly, we also have a web-based interface where this program just got run. And if you wanted to edit the program yourself, there is a live playpen where anybody can go and try out Rust programs themselves and edit them. So as I go through this talk, I may go link to this playpen, but more importantly, you'll be able to go, if you want to look at the examples yourself, and edit them in place within the playpen. This is totally editable code, which we'll now won't evaluate because I totally broke the input. Okay, so let's get back to the talk. So that was the motivation. We're doing this to work on Servo. And the goal here is to have a language for systems programming. I don't know how many of you have a background in systems programming, but it's a domain where having absolute control over the hardware and knowing what's going on it is super important. C and C++ dominate this space for the most part, and the systems programmers care about. It's nice to talk about algorithmic complexity, big O notation, and it's true, that matters, but system programmers care about both, being O of n or constant time, better still, but also about the last 10 to 50% of performance that sometimes gets left hanging. So, a tool that we want to be able to employ in a new programming language is sound type checking, and everyone in this room is probably aware of Milner's oft-quoted phrase, well, typed programs can't go wrong, and what sound type checking is about identifying a class of errors. That's what Milner was talking about, and then using the type system to remove them, or at least isolate them. And in fact, in more modern times, we can talk about an updated slogan, well-typed programs help assign blame. This fits into the Rust story a little bit because we don't necessarily stop the program from crashing. It's just that we delimit the parts of the code where it can possibly be the cause of such a thing happening. And even safe code can fail, but it has to be able to fail in a controlled manner, properly unwinding the stack and tearing down things properly. Okay, another thing that system programmers care about is being able to actually predict how their code is going to behave when it gets compiled. This is something that C programmers really love, to be able to actually visualize in their head what machine code is going to look like when they compile it. So that's important. So for Rust, we want to preserve that sort of simple relationship, but preserve memory safety and also not pay a runtime cost. We don't want to be boxing everything up, and we don't want to be having a GC managing everything, at least. Okay, so that's sort of the big picture motivation. Now, how are we going to get there? This is an ML workshop, so I felt obligated to at least, prove that I'm allowed to talk up here. So here's the top box is OCaml, the bottom box is Rust. I'm not going to spell this out because I don't have much time. There's a lot of stuff I want to get to. You're just going to have to trust me that the semantics of these things are roughly the same. Likewise, this is how you define a function in Rust. OCaml, Rust, very similar. And we have pattern binding, much like OCaml. Now, there's a playpen link. I won't follow this one. This program's too simple to do that, really, for. But the thing I do want to point out is that there's a couple things here that are different. Namely, one, you have to write types out explicitly on your functions, your top-level functions. The types need to be explicit. And also a type parameter stuck in there. The type parameters in Rust need to be explicit. That's what the capital A there is for. All right. And then we also have pattern matching, just like the ML family. The syntax is a little bit different, but you can see the analogy here. in terms of having an enum with two variants and some parametric polymorphism mixed in there. And again, I had to actually choose a type parameter. I could have made the combined function there polymorphic though, which I did here. And the thing I want to point out about this slide is that Rust has bounded polymorphism, like f-bounded polymorphism. So we don't use functors to accomplish the kind of genericity that you want in these cases. Instead, we basically have type classes. We call them traits. So here, the trait plus defines a method plus, and then you can use the method plus. So in the playpen, if I were to actually go to the playpen and run it, we get the final result 10 from combining 3 and 7 into one value. Okay. So the value model, though, is very different. Even though I just sort of try to claim that, oh, it's just like OCaml, don't worry. That's nonsense. So they're totally different in many important ways. In OCaml, when you pass large values around, they're heap allocated. They're almost always boxed, as far as I know. And so when you pass parameters around, that's just copying a single word of memory, and that's not the way it works in Rust. So here's a little puzzle for you all. Here I've defined that same enum that I had before. And if I ask about the size of a tuple with 5 elements, I get 5. So what's the natural response if I ask what the size of this ML thing over here is? Any quick, just anybody? Guesses?
1.
The answer is actually 2. But you were close. So it's because it's 2 words. This is going to be a pair of things. So this is how actually OCaml ends up representing one of these 2 things. All the other state that's in there is hidden behind boxed stuff, and all reported the size of that box over there. So that's how OCaml does things. And it's not how Rust does things. So if we did the same puzzle, you can implement the same code in Rust directly. We have a size up operator you can use. And if you do it in Rust, it actually ends up being 11, because the way Rust represents this 2 is it inlines the storage in place. Note, it inlines the storage in place, but also for an enum, it has to choose the size of the largest variant, which means that a 1 is also 11 words with a whole bunch of extras, useless stuff in the end, because there's only one occurrence of the A type parameter there. All right, so that's kind of interesting. So here are some implications of that choice that come up that may not be obvious in terms of having this focus on having storage be inlined, allocated in line. So this code doesn't compile. If I were to actually try to run this in the playpen, which you could do on your own time, I get this error, use of move value. And then it tells us, the compiler says, you've moved x in this line up here, the line W up there, it called f with x. And so it says, look, you moved x away, and it's not copyable, so I can't call y over, I can't call f again with the same argument, I've moved it away. Now some of you may read that and say, wait a minute, what happened? First of all, this sounds like linear affine types. You said move semantics, and you're right, this is very much like linear affine types. But the other thing is, didn't we already see some code that definitely reused x multiple times? What sleight of hand is going on here? And the answer is that this is not magic. It's the type system helping us, or rather the type and traits that we have. There's a copy bound that's used internally within the compiler as a trait bound that you can employ to say that this type actually is freely copyable. A sort of way of looking at this that I've come to appreciate lately is that everything gets moved. Even the stuff that's copied gets moved. It's just that the stuff that's copied, when you move it, it leaves a copy back where it came from. So the mental model of how parameters are passed and whatnot is you're always moving stuff around. But some of the stuff leaves old state behind, like breadcrumbs or something. Not really breadcrumbs, copies. So the important thing here is this copy bound, it's checked by the compiler. When we talk about things that are freely copyable, the compiler is going to make sure that it actually is things that are freely copyable. Things that can't be safely copied, like things that, for example, have pointers to own storage that's not meant to be shared, those can't be copied. That's, you're supposed to have only one reference to those things. But an integer, that can be freely copied, that's fine. So many built-in types implement this copy bound, but if you just have a type parameter with no trait bounds on it at all, that's not copied. And that explains the error message in the previous slide. When you set a type parameter with no copy bound, then you start getting errors like this. To make this really concrete, I could put the copy bound in explicitly, and then this code compiles just fine. But I'm not saying that that's actually the way you're supposed to program in Rust. That's not the way you're supposed to program in Rust. You're supposed to actually treat linearity and move semantics as being the starting point that you work with, because that is what's more general in terms of making your code generalized properly. Okay. So, all right, why am I talking so much about this move semantics business? Why does it even matter? I mean, there might be some cases where, sure, it might be nice to linearly pass things to know when you can deallocate them, but I mean, is that just for that? Is it just to get rid of some GC overhead? And the answer is no. This is not just about getting rid of GC overhead. There's a really important and perhaps subtle thing going on here. So, and unfortunately, to explain the problem, I have to explain how pointers work in Rust. So, in Rust, there are three kinds of refs. Okay, so in ML, when you want to have shared state that's mutable, you use ref sub, I believe, is the common way to do it. But when you are in a world that isn't about that, then you start thinking about references to data. And for us, there's three kind of core types that we could talk about today. There's things that are not references at all, so I'll just call that T, things that aren't pointers, integers, for example, or a function. You have shared references to data. That's what that ampersand T means. And you have a mutable unaliased reference, which is denoted by ampersand mut T. And all right, there's other kinds of pointers too. Namely, there's the star T, which stands for an unsafe pointer. We inherited that from C and C++. Those are pointers that are freely aliasable and freely shareable, and the deal is you can't dereference them safely. You have to dereference them inside an unsafe block because, hey, you might segfault if you do that. And there's other kinds of smart pointers, but they're all implemented as library types, so I'm not going to talk too much about them. The point is that in terms of reasoning about things, you can just think about the top three bullets there. Okay, so in terms of how shared references work, this is sort of some example code where we allocate a pair on the stack, and then we can take reference to some part of it. So you can actually reference into the piece of code the bit of state that's allocated on the stack, and then take a pointer to that integer. And you can freely make copies of that reference to an integer because, as I said before, ampersand T implements the copy bound, or rather, it's freely shareable. So this works. You can run it. And then you could have potentially mutable unaliased references. So here I have some code that has some local state called x with this mut attribute on it. What the mut thing means is that this thing is now allowed to be mutated. It's some stack allocated state x there that's allowed to be mutated. And then I could actually take mutable references to x, that's what the ampersand mut means, and do things like increment it. And if you do this, you'll actually get 6 out after you run that block of code. And as you'd expect, now you can't freely duplicate these kinds of mutable references because that's the whole point. They are unaliased. Okay, so this leads to an interesting language feature that I didn't understand for a while. I said we had pattern matching before, but the problem is that the way pattern matching works semantically in our language definition is that when you do this pattern matching, it actually moves stuff. It conceptually moves them into new stack slots. So when I match P here, it's going to try to move the contents of P into new stack slots for A and B, at least in the abstract model. It could be the compiler manages to optimize that away and reuse the same stack slot. But in terms of what the compiler is going to reason about, it thinks about move. And thus, it tells you, you cannot do this. The compiler rejects this code, saying it is illegal to try to move the contents of P out, because within the body of this match block, you attempt to take a reference into P. So it's been moved away. Well, how can we write code like this then? What are we going to do if we want to match on something but also talk about references to its internals? And the way Rust handles this is with a new variant on patterns, namely ref patterns, where now if you have a ref pattern, now you can actually match on P where it doesn't move its contents out. It leaves P in place and takes references into its interior. And when you do this, now you can still take references based on the path P, that's paths that are rooted at P, and also have refer to B here, which I don't know if it was clear in the earlier slide. Here, B is bound to something of type int, I think, or type B, I guess, which ends up being type T. Yeah, cat T. That's what B is. So in this context, B is bound to a capital T. It moved into that. In this context, B is now bound to a reference to a T, shareable one at that. A little subtle. Okay, so there's this ref thing. It means that you don't move stuff away. And okay, why do we need this? why do we need to have this thing, and how does that play into this aliasing story that I was talking about before? Well, the answer is this is all for type soundness. It is not, again, about trying to avoid GC allocations. This is about actually having the system behave in a sound fashion. And the reason is this. If you have mutable aliasing, it introduces type soundness holes, where you can totally break things. So here's some code where I've got an enum with two variants. One that has a function, that's the A variant, that takes a function from int to int, and one that just has normal int. Okay, so I could create two instances of this variant, of this enum. On the left-hand side, we have the one that's called A, and on the right-hand side, we have the one that's called B. And they're, the two matches the two variants, A and B. One has a function, one's carrying a function, one's carrying an integer. Watch what happens here. So when I call foo, I pass in the A and B, they're named M1 and M2. They're down to the parameters P1 and P2. And okay, what I'm going to do here is I'm going to overwrite P2 with the state bad code. And when I run this, what happens? I'm not going to run it in the system right now. Actually, it's fine. This is actually no problem at all. So this will run just fine, and nothing bad happens. So, okay, what's the deal then? Well, the point is, watch what happens to small variations on this code. For example, instead of assigning P2, what if I were to assign a P1 in here? Remember, I've matched P by reference. I have a reference to some code that's supposed to be called, a function adder, and then I overwrite in place what P1 is bound to. This effectively is overwriting the code pointer that we were going to run with this random integer that probably is not a pointer to code you can run. And in fact could be some sort of attack from an attacker to take over your computer. And if you try to run this, what happens? Well, the answer is that, in fact, the compiler rejects it. It tells you you're not allowed to do this. And the reason is because it would violate the rules I was talking about earlier in terms of aliasing. Particularly, let me show you what the compiler error looks like. So if I try to run this, oh wait, hold on, wrong slide. That would be bad. It's this slide that I was trying to show you. This one. Yes. Yes. It says, the error tells you cannot assign to the path star P1 because it's been borrowed already. The match up here, P1, borrowed it. And that borrowing means you cannot overwrite its state mutably.
Is the borrowing first order? Can I load the borrowed pointer on something else afterwards?
Yes. Yes, it's scoped in that you can't escape the local scope, which I think I'll get into hopefully soon, but you can pass it along. Okay, so the compiler rejects this case, but you can look at this and be like, oh yeah, but that's a local analysis can look at this and tell that's clearly bad. That's clearly wrong. Oh, okay. So what happened before? I actually wanted to concretely demonstrate that this actually is totally unsafe, and so I put an unsafe block with an unsafe pointer and assigned a random integer. That's why earlier when I ran the playpen, we actually saw a crash. This segment faulted because I hacked another type system with an unsafe block with something that's just totally bogus. So yeah, unsafe blocks. The message here is it means it can crash. Don't. If you see it, don't trust it. That includes in the servo code, yes. Okay, so all right, now watch this. So okay, this is the same example from before. The Rus Compiler will accept this. Watch very carefully. Oh wait, nothing changed. Something changed. What changed? This is where the aliasing get introduced. Is if you pass M1 twice. So this is still rejected by the compiler though. It's going to say again, you cannot borrow M1 is mutable more than once at a time. The compiler is smart enough the type system is smart enough to tell you this was an illegal thing to try to do. And it's all tied into what I was talking about earlier in terms of having a move semantics. A linear type system / move semantics gives you the ability to reason about aliasing, and we need it. When you have this kind of in-memory shared representations of things, you need to be able to reason about this. Okay. So this ties into the question earlier. I claimed earlier that &t is a shared reference, and does this mean you could actually copy it anywhere you like at all? No, that would be complete nonsense because then you'd end up with dangling pointers. So you can't just put it anywhere you like, willy-nilly. So instead, when I showed before, the core types were either ampersand T and ampersand mu T. I fudged it a little bit and lied. The real answer is that they are ampersand tick A T and ampersand tick B mu T, where tick ident denotes a lifetime. We call it lifetime within the Rus community right now. But it's similar to the region systems that were pioneered by Toft and Talton. So the point is that ampersand tick AT means that X is a reference that'll survive at least as long as tick A, and perhaps it'll last even longer. And if that reference survives that long, implicitly T is going to be forced to also live that long. Okay, and this part of the language then has bearing on other parts of the language. For example, when you have a function that's parameterized over things with these hidden lifetimes, this is actually the sugar for something that's actually parameterized over the lifetimes in question. So I'm showing that here with explicit generics. You could write this out explicitly if you wanted to, but more importantly, if you wanted to, you could write out it with a single tick A. If you had the constraint that lifetimes would be the same, you can express that. It's not in the sugar form. You'd have to write the desugar form to get it, but you can express it. And also, if you didn't want it to be the same, if you want to have some relationship, you can also express that. You can put bounds like this, saying that quote B, so the lifetime B has to live at least as long as lifetime A. This is actually a really recent addition to the language, being able to express this directly in this fashion. So it's super exciting, because it means certain kinds of code patterns you couldn't write before, we can do now easily. So earlier in my examples, I showed some structs. You may have noticed I didn't put any references inside of structs. And the reason is part of the language, you have to use lifetimes explicitly. You can't use sugar in this case when you have structures. So when you have a structure, if it has references, you have to put the lifetimes explicitly as part of the structure definition. When you create instances of the structure, you can omit them, but not at the structure definition level. I just want to point that out because it might matter in the slide to come. So, all right, well, some of you may have heard of linear type systems before, and you might be saying, oh, wow, they're kind of painful to work in, not fun to program in. Are you going to force me to use linear types every time I want to mutate anything at all? And the answer that we have right now is that it's not quite like that. There's two kinds of mutability in Rust. Right now, the community's come up with the terms inherited mutability and interior mutability, where inherited mutability is the default, and interior mutability is this other special thing that's still sound. It's still absolutely sound, and it still prevents data races. I don't know if I actually mentioned that was one of the goals for us, is to be totally data race free, but that is, in fact, one of the goals. So, but we don't want to just artificially hamstring developers. So, there's some examples here about inherited mutability. Oh man, time. Does anyone know? So, I don't want to waste time spelling it out. Am I over time? Or? No. Okay, well then I'm not going to spend too much time going over this. The point is that the reason why it's called inherited mutability is that when you have a chain of references, if you're going to try to mutate something, you have to have the mute keyword all the way down the chain. So the way mutability works is you don't have to mark fields as mutable or not. Instead, mutability comes from whoever owns the data, and if you have, or rather whoever has exclusive access to it. And the way you denote exclusive access is with this mute keyword. So there's a whole bunch of examples of things where someone tries to mutate u.p.x and it doesn't work because someone's missing a mute. So I'm going to just go through these examples because you can see them in the slides when I post them. So the point here is that if you own something or have exclusive access to it, then you get to modify it via inherited mutability. You just might have to do a little bit of shuffling in terms of taking your local variable and moving it into a mute slot. But other than that, you don't have to, or rather change your code even. Okay, but the inverse does not necessarily hold. The inverse of the statements at the top about owning, implying modifiability, it doesn't mean that if you don't own something, you can't modify it at all. That is not a valid claim about Rust. Because we also offer interior mutability, where these library types they offer, cell and ref cell, offer ways to mutate state without requiring unique exclusive access. So there's cell, where the contents must implement copy, and then there's ref cell, where the contents don't have to be copied, they could just be things with arbitrary state. But for that, for using ref cell, you have to claim temporary exclusive access, and then there's dynamic checks in place to check whether, when you attempt to mutate it, that you actually were the exclusive owner. And if you're not, then you get a dynamic task failure. Not a seg fault, but a clean shutdown of the system where it destroys things. That's important, an important distinction. And then there's some sample code here to illustrate something very much like what I posted earlier, sort of, but to argue that this code just runs fine. I'm using shared references, but it's okay to mutate P2 and then later do P1.get because these things are cells, and cells force their contents to be copyable. In particular, notice that in this case, A is not holding a code pointer. It's just holding an integer. It's free. It's okay to copy that. Okay, so like I said before, the mute keyword is just meant to mark these paths, and most importantly, it doesn't. Even though it says mute, and oftentimes when I first saw the language, I thought mute meant this is the only way to mutate things, but it doesn't actually denote that. A lot of people use it that way. It's the way it often is used. It's the way we meet for people to use it. But the denotation is just that I want exclusive access to this value or this path or whatever for some operation. It might not even be mutation. It might be some other thing you're doing that needs exclusive access for this whatever you're trying to represent. Okay, so I haven't covered a bunch of stuff. We can talk about it offline. In particular, the most important thing I want to point out here, I was careful in this talk not to show any closures. But that's not because they're unsound or anything, it's just because I don't have time to explain the rules. But Rust does have closures. Every function I showed earlier had no free variables, but you can have a function with free variables. Okay, that's all.
So I'm wondering how the work on Rust connects to the earlier work on Cyclone, where it seems like they were targeting something very similar and used a bunch of related techniques. But I think from Greg's point of view at the end, they sort of felt like they didn't come up with something that was really usable. And I'm curious what you guys know about the Cyclone work and what you think you did differently.
So we definitely are aware of the Cyclone work. I think the big difference is that I believe for Cyclone, at least the part of the point was to try to hew very close to the semantics of, or at least the appearance of C. And C++ was Cyclone, it was only C, right? Or was it C++ as well?
I believe it was just C.
Okay, well in that case, fine. Hew very close to C and C-style programming. And with Rust, we aren't attempting to do that at all. I shouldn't say at all. There's definitely some things inspired by C and C++. Yes, semicolons. I was actually going to say RAII is something that we've taken from C++ as a certain kind of style of programming that we are inspired by. But we are more than happy to throw away ideas that get in the way of making it easy to write programs that satisfy these rules. So I think that might be a reason why we're hitting a better sweet spot, because we're not hindered by that.
Yeah, it's worth saying in the end, they started adding variants and other things like that. So they started over time walking farther, and indeed found that to be very valuable. And maybe it's worth more communication between them to see what lessons there are.
Yeah.
Sorry, that was a great talk. One of the things I've noticed about linearity in the past is that whenever any large-scale systems code is built using it, it's like Singularity from Microsoft, the operating system, the linearity eventually leads to the death of the system because it tends to taint any large-scale code base with linear channels or some kind of notion of constraint that propagates beyond modular boundaries. So whenever you're building something as big as Servo, you must have some way to constrain linearity between components so that it stops. So is this done through process separation or something else, or do you just not deal with this as a problem at all?
I'm not sure if I'm the best person to answer that question, to be honest with you, because I don't know if I feel like that. Well, okay, in the Rus Compiler, which is the biggest piece of code that is written in Rust, it's bootstrapped itself, in case I didn't say that earlier. It's very cool to work on this because it's bootstrapped itself. But we definitely are actively breaking some rules ourselves internally, perhaps because of issues like this, quite arguably. So yes, part of what you can do is you can use unsafe pointers and whatnot to break the rules to get around that kind of thing. So that's one answer. It may be the best answer. Lars, do you have any other inputs on this?
He didn't talk at all about it, but there's also a lightweight task system and concurrency similarly, and sort of the linearity is, it works very cleanly with the concurrency model. So in practice, we can write safe systems, and the only time we really fall into unsafe code is when we have some horrible performance guarantee that we need for the web platform, where we say, okay, we may have to violate some constraints here. But in practice, we haven't had too many problems with that.
Oh, good. I'd love to see a tutorial on Rust.
There's one tomorrow.
Tomorrow morning. No,
At 9 a.m. If anybody was they're interested, piqued by this, show up bright and early.
How do you know you have a sound type system?
We don't have a proof yet. We have some people working on it. We have some thoughts about it. At this point, we're still in the mode of, I think, just even coming up with an operational semantics that's small enough to to have those kinds of type semantics arguments applied to them. So there's some work on, for example, developing a Redux model, and also I think that some people are playing with using Coq, but I don't know how far along that really is. But we don't know. Right now, it's all informal arguments. We definitely have broken. I mean, there's parts where it's definitely broken still.